Okay, good morning. Last session before lunch on the last day. I will be on time. If I get to the end of the time, I'm just going to stop talking. My name's Dan Marshall. I'm with Wells Fargo, part of the big data development team within the big data corporate team. And I want to talk today about functional programming and big data. So basically, just taking a look at functional programming from a definition standpoint. What is it? How does it compare to some of the other programming models? Try to make a connection between not just functional programming, but also functional thinking and big data. And then we'll look at a very simple case study that was an actual case study that we ran into at the bank, where the application of functional thinking helped solve a performance problem. So functional programming, as we all know, it's brand new, it's shiny, it's the latest thing. Yippee. Not so much. The concepts were introduced in the 1930s with lambda calculus. The Lisp language, created at MIT in 1958, is an early functional programming model. So the point here is that it's been around a while. It may be new and shiny to some of us in the data area because it's getting applied more and more within the big data realm, and we're hearing more and more about it, but it has been around a long time. In fact, when Google came up with the original MapReduce research, they based a lot of that on functional programming principles that were already very well established. So I made three very coarse categories here. This is not an academic presentation, so we could argue with every one of these points. I'm trying to keep this very general. So we can think in terms of pure functional languages, things like Lisp, Haskell, F#, Erlang, some of those messages that may be new to some of you, or maybe you're just starting to explore them. Or if you come from another domain, maybe you've been using these for years outside of big data. What's interesting about pure functional languages, you can make the case that they can be mathematically proven to be correct. All right? So if I instruct the program to do something, it's going to do it, and I can prove it. As opposed to, if you're in the Java world, we have things called design patterns, which have evolved over time based on errors that have been made, mistakes, lessons learned, and they developed into these patterns of development that we use to try to minimize issues and try to make sure that things are going to work as instructed. There's a second category here, which I'm going to call hybrids, because they're not purely functional, but we can think of them as functional languages, and certainly we think of them that way within the big data world. Scala is the most prominent, and Clojure, I think, is something you'll be hearing more about as we move forward. Scala, of course, is the basis for Spark, and you're starting to see it emerge in some of the other frameworks as well. And then there's non-functional. So I say mostly non-functional. There are things happening with some of the languages like Java and Python where functional programming aspects are working their way into the language. Most notably in Java, you'll be hearing a lot in Java 8 about lambdas, things like that. In Python, today you can write functional style programming, but you don't necessarily have to. So at the top, you have no choice. You will be functional. In the middle, you should be, but you don't necessarily have to be. And down here, you kind of have to work at it. So in this presentation, like I said, we're not going to talk academics. Like this little guy in the corner. I get up in the morning, I grab my lunch pail, and I go build Hadoop systems, right? I don't sit around all day and argue about, we're not pure methodology and this and that. The real bottom line is, are we going to produce systems that our users can use? And that's what we try to do. So my point here today is to think functionally is the most important to start. It doesn't mean you have to run out of the room and go learn a new language, but you can apply some functional thinking to what you're doing today. So I've pulled out some of the characteristics of functional programming. There's a lot more to talk about, but for today we're just going to talk about these bullet points. What makes a programming model functional? Probably the most important thing is the idea that functions are first-class citizens. They can be used in the code like any other variable. So if you come from another discipline and you're used to variables being an integer or a string or this or that, you can have a variable that's a function. And that can be passed to other functions. It can be returned as a result of a function. It's basically just another first-class part of your code. Functional programming is also characterized by the fact that these functions are called pure functions. And as such, they produce no side effects. And what that means is that when you run it, it does what it says it's going to do. It doesn't do anything different. You don't have any unexpected behavior. And because you don't have unexpected behavior and no side effects, and this is an important point in the big data world, it helps facilitate parallel concurrent operations. It also helps with giving you the ability to do optimizations if it makes sense, either you or the compiler or the runtime. It should be intuitive that there are side effects and you're running things in parallel, then you've got cross-communication, you've got issues, and you try to avoid that at all costs. We'll talk a little bit about recursion as an alternative to iteration, commonly known as looping as an example of that. We'll talk about immutability, which is the idea of avoiding changing state and trying to avoid as much as possible mutable data or data that changes. And functional programming tends to be declarative versus imperative, so it's more a matter of telling the system what to do as opposed to how to do it. So let's look at each one of those one at a time. And we'll start with a simple code example, and don't worry if you're not a Scala programmer. Hopefully we can get some of these concepts across, and hopefully you can read it. In this simple example, we start off with a value of a name list, and this is a list of people. Let's say these are the people at the Hadoop Summit. So this year we had Dan, Sally, and Joel. And as I'm in my interactive environment here, the environment just kind of prints out that list over here, so that verifies that I've set that up properly. I'm doing a function definition here called len_summit_names that takes a string and produces the length of that string. And this def statement probably looks very similar to other programming languages. You see something similar in Python. This could be a class and method definition in Java. So nothing really new under the sun here. The next statement is an alternative to that, in which case I'm defining a value, which is kind of like a final variable. I'm calling it len_summits_2, and it does something similar. It takes in a string, and it operates to get the length of that string. The notation here with this arrow indicates that this is a function. But in this case, I'm assigning that function to a variable name as opposed to defining it as a discrete item here. So in this case, I can take the name list that we started with, Dan, Sally, and Joel, and I do a map operation. And into that, I pass the name of that defined function up here. And over here on the right, what basically is happening is Dan has 3 characters, Sally 5, Joel 4. So I get a list of integers 3, 5, and 4. Very exciting. And then for each one of those, I print it out. Alternatively, I'm showing the other variable being passed in instead of the function. And in this case, len_summit_2 produces the same results, as you would expect. But what might be a little interesting here is that this variable is being passed into another function called map to do some work. So that function len_summit_names_2 is a first-class citizen of this program, and we can use it just like any other variable. Further, I may take that list that I created up above, this NL, and I could do a reduce operation on. In this case, I'm doing something called reduce left. I pass it in a couple of variables. We see that arrow notation again. And basically, I'm defining what this function is going to do here. And I'm saying if A is greater than B, return A, otherwise return B. Basically, I'm trying to find which name has the most number of characters in it. What's the maximum length? So again, I pass in length summit names. In this case, you can interchange these. I'm using this one this time. I'm doing the reduce left. I'm passing in the max parameter, which is a Scala reserved word, and I get the answer. And in case you're wondering, there is a simpler way to do this in Scala. Just say nl.max. But the point is, if you were writing your own function for which there wasn't something built in, then you would do something similar. You would just write the code yourself. What's sort of semi-interesting about this example, if you're new to this, is that you see things like map and reduce, which should sound familiar at this point, unless you've been in a cave in Borneo. And that's nothing new in functional programming. Again, mapping and reducing has been happening in these algorithms for decades. And what's kind of might be new to some of you is that now it's happening at scale on Hadoop. So no, Google did not invent MapReduce, but they exploited it. And here's all the animation that I should have been showing you when I was talking before. So take a moment to enjoy this as I go through it. That was about 3 hours worth of work. Okay, so here's an example in Python. I'm glad I spent that time. Yeah. Here's a Python example, just to show you can apply these principles in what we would typically call a non-functional language, but it kind of looks the same. So I start off with a name list, Dan, Sally, and Joel. In this case, I'm using the lambda keyword. And what that means is that I'm defining this function called lenSummitNames to take in an attendee and get the length of the attendee. And Python is not a typed language, so you notice I don't have to say it's a string. It's just a thing, and Python will figure it out. I'm defining another lambda here under this variable name, maxSummitName. I pass in an x and a y, and I do the same kind of logic. And then we get name lengths. We do a map, which is a Python verb or Python method. We pass in the length of the SummitNames function. We pass in the name list. And the answer we get back is the name lengths. So we get 354. And again, we can do a reduce operation on that as well by passing in the maxSummitName function, the name lengths list that we created over here. Then we print out the answer 5. You could write this Python program without using map and reduce with for loops, and it would work just as well. But you can start doing this today. So even if you're saying, well, I'm a Java guy, I'm a Python guy or gal, I don't have time to learn Scala, you can still start to kind of bridge the gap by using some of these Lambda type things in Java 8 and in Python today. Okay, the other kind of principle here with functional language is the idea of pure functions. What it really means is that when I apply a function, for example, y equals function of x, it always evaluates the same result given the same argument values. It can't depend on any hidden values. It can't mutate any state that's unexpected. Now you would look at that and say, well, why would it do anything different? But if you've ever programmed 10 lines of code, you know why it would do something different. Maybe there's a timestamp that you're looking at. Maybe there's another thread that's influencing one of the variables that you're using in that function. In a lot of languages, anything could go wrong, and you can't guarantee that if I put in, let's say I put in a 10 to this function, that I'm going to get out a 20. I might get it one time, the next time I might get 21, the next time I might get 22. In a pure functional language, if you put in a 10, you're going to get a 20, whether you call it one time or a billion times. It's always going to be guaranteed to be the same. It does not, and the second bullet talks about does not cause any semantically observable side effects or mutation of mutable objects, which is a fancy way of saying it's not going to do anything different. So knowing that, and you're thinking about doing things in parallel, that gives you as a programmer and also the runtime and compile system good information to use when it's encountering these things. So imagine you're doing a job that's processing 1 billion records, and out of 100 million of those, you call that function with a 10. You can really evaluate it once, find out that it's a 20, cache that, and then the other 499, 999 times you run it, it just returns a 20. So it doesn't even bother to run the function, because it's guaranteed to bring back the right result. So hopefully you can see that that might be an optimization. Imagine this function is doing a whole bunch of stuff, right? It's 1,000 lines of code. You just avoided all that 500 million minus 1 times. It's referentially transparent, so as I just said, that means you can cache it and reuse it safely without having to worry about recomputing it. Also, these languages do lazy evaluation. So because there's no guarantee, there's guarantee of no side effect, you might even be able to skip a function sometimes. So imagine you had something like a conditional trigraph where you had a condition, then you had true and false. In some languages, you actually have to evaluate the true and the false before you apply the condition to make sure that if there's any side effects, that those would either happen or not happen. In functional programming, it might skip the true case and just do the false case if it's already done the true case or if it's already cached, things like that. Or it won't even bother in some cases to even do it the first time if it doesn't have to. And that's important when you're operating in parallel, whether on the same chip or across a Hadoop cluster. So really, in a pure function, if you can ask the question, what might this function do that I'm not aware of? In a non-functional language, you can't really safely say, I feel like it's not going to do something. You always have to be careful. So recursion is an important concept in computer science. It's a big topic. It could be a topic all on its own. Just for today's discussion, I'm going to keep it simple and just talk about recursion versus iteration as an example of how you can use recursion in functional programming. So we're going to iterate without mutating, which always sounds funny when I say it. I mean, who'd want to mutate when they're iterating, right? Somebody might be watching, right? Tail call optimization to avoid blowing out the stack. So if you're a programmer and you're thinking about recursion algorithms, you're thinking it's going to push it into the stack and we're going to run out of stack memory. Functional programs don't do that. They have different kinds of optimizations to avoid that. So that's not really an issue. And this is important all the time. You always want simpler code, right? Code that's easier to look at. So what I did was I created a bad, good, and a better example. So here's the bad example, which probably doesn't look too bad to most programmers, but here's a for loop. I've got a variable x. I'm starting at 0. X is less than the length of my list, x plus plus, curly bracket, my list, blah, blah. So do something with x and produce my list 2 from my list 1, or my list. Not really complicated, but it illustrates the point that I have to mutate x to get through this thing, right? All I really want to do is take a list, do something to it, and produce another list. I got to remember, where does the curly bracket go? Does it go there, or does it go over here? Is it curly, or is it straight? There's a lot of noise in this program, right? It has nothing to do with the problem I'm trying to solve. And geez, is it 0-based, or is it 1-based? And do I do plus plus x, or x plus plus, right? Nothing to do with the problem you're trying to solve. A lot of languages have some kind of an enhanced for loop now that looks maybe something like that. So here you're not explicitly mutating it. It's still being mutated, but you're not trying to keep track of all this noise. And this is a little bit better. So for every variable in that list, do something to produce my list 2. But at the bottom is the functional way of doing it, which is even better, which says my list 2 equals map over do something to my list, right? So it almost reads like I'm telling it what to do, and it's going to do what I tell it to do. 1 line of code, 2 lines of code, 3 lines of code. A lot of syntactic stuff here that doesn't really matter that's introduced. And this is a simple example. Clearly, this example can get more complicated, but as it does, this doesn't really get a lot more complicated. And I think maybe at some of the sessions this week you might have seen comparisons of Java MapReduce to Scala. It's always kind of the same thing. There's 18 pages of Java and there's like 4 lines of Scala, right? That's not an accident. That's because functional programming helps you do these kind of things. So recursion is kind of a functional alternative to mutation. Immutability is an important concept. So once an object is created, it cannot be changed. Thread safety is no longer an issue, as we talked about earlier. Mutations produce side effects some of you don't even know about. Those are the ones that are the hardest to debug. And the code is more maintainable. It just sort of does what it does. So if you can count on that immutability, you don't have to remember to put final modifiers on it or worry about those kind of things. You just know it's going to be immutable. So here's a simple example, conventional programming. I've got my friend the for loop. I'm doing something. And maybe this is working fine, and then somebody says, you know, we need to multi-thread this. So they create a multi-threaded program without changing anything else. Now one of my threads is processing this, and meanwhile another thread has messed around with my list, and I get unpredictable results. This is the kind of thing you can guarantee won't happen if you're in functional programming. So here's kind of a thought for the day. But you might be hearing a lot about CRUD operations in Hive and what's wrong with HDFS, why can't I write to it? So in the context of immutability being a good thing, you know, have you heard this? Have you heard people saying things like HDFS is broken, I can't change a file, will somebody hurry up and fix it? Anybody heard that before? Right. So it may not be a bad thing that it's immutable. And that's an interesting topic to discuss. I don't have on the chart, but there's a paper that's titled Immutability Changes Everything by a gentleman named Pat Helland, Helland. So if you want to read more about this whole topic of is immutability good or bad, it's an interesting paper. And it's an interesting title if you think about it. Immutability changes everything. You get that? Yeah. Took me a while. Very clever. So historically, functional programming has worked very well in what's called data-centric applications before the days of big data. And that's kind of a well-known thing. But big data, as we all in this room know, tends to be highly data-centric, right? It's all about the data. It's not about the processing. So these two seem to be kind of trying to solve the same problem. So let's look at our friend MapReduce. Has anybody seen a picture like this before? Before lunch? Yeah. So we have mappers. We have reducers. We have our friend the shuffle. We have HDFS, our immutable data store. And we typically will pass a function to it. If you're a Hive program, you're really doing this under the covers. If you're writing Java MapReduce, whatever, you're packaging something up and sending it to the data. So this is an important concept that you're shipping the function to the data, which is, when Hadoop first came out and we're all kind of learning it, that was one of the first ahas you had to get was, this is not like Oracle or Teradata where I'm the client, go get me all the data and bring it back and I'll work on it, right? Now we're saying, here's the code, go find the data and do something. That's a different paradigm shift. I didn't want to say paradigm shift. That's a different way of thinking about things, right? Paradigm shift is so 90s. Yeah. So we ship function to the data and go do some work. So I just kind of borrowed one of the lines of code from the previous example here, where we talked about mapping a function to a list to produce another list. And really, that's what's happening with the mappers, right? This jar file is being applied to each mapper independently. It's doing its work, and it's producing another list, which is the intermediate results to be passed on to the reducer. So again, nothing new under the sun for functional programming, but this is the model that's kind of evolved in the first phase of Hadoop, the MapReduce phase. And again, it's shipping function to data as opposed to the other way around. And by the time it gets over to the reducers, I'm going to produce another list, another immutable list, given an immutable list, list 2, which I created over here. I'm going to apply something like some kind of reduction operation. In this case, I'm showing reduce left, but it could be whatever it is. And this max is whatever your code's trying to do to produce the reduce output. So if you kind of look at that picture and look at the 5 things that I talked about earlier, or some subset of them, this whole infrastructure of Hadoop MapReduce is based on immutability. There's a lot of recursion that goes on. It's very function-oriented. Parallelism is the basis of what it does. And there's no side effects. So if this mapper is running and mapper number 7 over here fails, mapper 1 doesn't care. And mapper 7 can't do something or mutate some data that's going to impact how mapper 1 is going to perform. So they're all operating independently in parallel. So I make the case here that if you look at this, it's a good match for functional programming. Functional programming loves big data. So at the count of 3, everybody say aw. Ready? 1, 2, 3. Aw. Thanks. Match made in heaven, right? So I'm warning that here's my opinion tags. Everything within those tags are opinions. But if we look at what I'll roughly call generation 1, 2, or 3 of Hadoop, we're kind of exiting 1 and going to 2 now, as you can tell by a lot of the topics here. Some of the things you might do, transform data, flow data through a series of steps, complex event processing and messaging. In Gen 1, we did most of this in Java. Maybe we threw in some Pig, some Hive, but a lot of it was Java-based. That's what we knew. That's what Hadoop was built in, so we got started. But you could say it's a little bit of a mismatch in styles and in models as opposed to functional programming. And what we're seeing now in what I'm calling Gen 2 here is that you're starting to see Scala, not so much Clojure yet. Clojure is kind of under the covers in some cases, but as far as what we're developing on, it's more and more kind of pointing us towards Scala, right? Spark, how many Spark sessions this week? Probably about 30 or 40. That's based on Scala, built in Scala as the primary language. And even when you sit down to first do the Spark tutorial, you'll do it in Scala, and you'll say, that was easy. And then you do it in Python, and you say, and you do it in Java, go, what am I doing in Java for, right? So you're already feeling that mismatch, so why not just use Scala? So my contention is that Scala has become more and more important. If you're a Java programmer today and you don't know Scala, it's probably time to learn. And if you don't have time to go to class, in your next application, just do it in Scala anyway. That's the best way to learn it, right? And the interesting thing about conferences like this is you learn so much so fast. I just walked out of a session that Gwen Shapiro was doing where she talked about Hummingbird as a way to do this. And of course, we had to do these charts like 30 days ago, so I didn't even hear about it. So within the last hour, I've learned something new about, the Gen 2 column. So if functional programming is a good match for MapReduce, it's probably even a better map for things like the Spark framework, right? So managing large bunch of data has taken us from MapReduce to Spark. Spark is based on functional programming, so we're kind of going that way, right? We're being taken in that direction. And then who knows how long this will take, but we might all be doing Clojure in 4 or 5 years, or maybe we'll still be doing Scala, or we'll be doing something that we don't know about yet that'll be next year's 20 sessions, right? But I think whatever it is, it's going to be closely mapped to the historical functional programming paradigm. I said paradigm again. So we're going to gravitate to the same language, I think, for common sense reasons. Because it's a good match, and because it's obviously easier to manage a development shop if you don't have a bunch of different languages. And one of the things that I heard in that last session about Hummingbird was it helps do some of this, where not only can you use the same language, but you don't have to rewrite the code. You can rewrite the code that you've written in the same language across different kind of batch or streaming architectures. So things will get increasingly functional over time, just as a natural progression that we're seeing. And I think eventually, who knows when, over here someplace, that the frameworks will just kind of disappear into the language. You'll have a list you need to process, you'll write a functional program, and you'll get a new list out, and you don't care what's under the covers. MapReduce, Spark, thing to be determined later. It'll all be invisible at some point. End of opinions. All right. So here's a case study. Now, what's interesting about this, I think, is that this doesn't really get into any specific functional programming language. This was an example of applying functional thinking to a problem using conventional technologies. So in this simple, I simplified the example, obviously, for this session, but basically, we have a Hadoop job to scan transactions within a date range specified to a script. So for example, I want to process the month of February 2014 when I run this script. I want to output a record for each transaction within that range that has a close date within the range, and if so, I write out a type closed. If I have an open date, I write out a type of opened. And if one record has both dates, I output two records. So in this example, customer 101 has an open date within the range. All the green ones are within the range. So it gets a record out of opened. Customer 202 has a closed date within the range, so he gets a closed. Customer 303 opened and closed accounts in February, so he gets one line of open and one line of closed. And customer 404 didn't fall within the date, so he drops out of the results set. Okay? So here comes my list in, here comes my list out. Pretty simple problem. So version 1 of this, the developer wrote a bash script with a lot of data arithmetic. And the first thing I noticed as I looked at this was it was kind of loopy, right? There was a loop within a loop, and they were dividing dates by 86,400 to get the number of seconds in a day. You know, it gave me a headache. But it was a lot of noise just to get to the point where you call the pig script, right? And my contention here is that in version 1, the developer who looked at this was very conventional, very procedural, and they kind of wanted to have data come to the process. So they actually created multiple for loops in this Unix script. They had two different versions of the pig script that were 99% the same, except for a couple of lines of code said open or closed. So that didn't pass the smell test right off the bat from a software engineering standpoint. Basically, he would call this thing once per day in the range. So for 28 days in the month, this thing looped around doing data arithmetic and called the pig script 56 times, once for each day, once for open, once for closed. So he filtered the input by the date. We had a Java user-defined function to do some transformations that would assign that closed open type. And the outputs were merged to a directory outside of pig and then brought back into pig into the same directory. Now, the results were 100% correct from a business standpoint. So we all declared victory and went on to the next job, right? And it ran for a while. It took about 16 hours to do a month. But it ran overnight. We had capacity, who cares? Then we started to have some constraints on the machine. We were running out of windows. So we started to go back to look at some of these early scripts to see if we could make them run any faster. Another thing this thing was doing was global state in those dates. So we talked about, you know, mutability and not maintaining global state, but there was a lot of stuff going on in these scripts outside of pig that might impact the pig. And the programmer also looked at this as a tuple in and a tuple out problem. So in the pig script, if we go back a couple of charts here, this example here, the 303, during the code review, I said, well, why didn't you write out two tuples instead of one? He said, well, you can't do that. Right? So record came in, record went out. That's why I need two scripts, right? So it wasn't thinking in terms of a list coming in and a list going out. He was thinking in terms of almost like file I/O, right? Loopy, global state, tuple in, tuple out. So we kind of refactored it, looking at it as a kind of a functional problem. So now we pass the date, the same kind of date we pass in the same way, but we only call one script one time. So basically letting the Hadoop infrastructure do all the heavy lifting of figuring out which dates to do, move that work into the cluster. We filter, the pig script filters by closed or open date. So if either or both match, it's going to emit a row in that one pass by having the Java UDF assign one or two types depending on the date values. So when you're doing list processing, you've got a number of items coming in of n, and the list out can be 0n or greater than n, right? There's nothing that says I have 4n, 4 have to come out. And you all know that. If you think about it as applying operations to a list, the number in and number out are not significant. It's only what you do. So results compared to version 1, they matched exactly. Unless I ran it late in the day, then it didn't work. So we had I thought of this as an immutable list in and a new immutable list out. And this is the important distinction that was made. In the UDF, we took a tuple in and we put a bag out. So in the pig world, the bag is kind of like a grouping of tuples. And then by using the flattened verb in pig, we would take however many tuples there were. In this case, there's only 2, but you could obviously have a problem that could have greater than 2. In this case, the most you could have was 2. It's either 1 or 2. But if you had 2, you would put out a bag with 2 items in it, flatten that bag, and then you'd end up with 2 rows in your pig script, right? Pretty simple if you know pig. In the functional programming world, we would call this a flat map, where we take the distinction of multiple tuples and remove the tuple distinction and just create a list of things. So a single list comes back out. You can think of it as pivoting it and then creating multiple rows on the way out. The date was passed once as an argument. There was no date arithmetic. There was no kind of noise before you actually got to the real work. Whoops. So let's talk about the side effect. When I first ran this, I took the date range, I captured the results, and then I ran my version of it and captured the results byte for byte and looked at them. In the first test I ran, everything worked perfectly, so we had a replacement for the functionality. But then I said, let me run another test, and it was late at night, maybe 10 o'clock at night, and I ran another one, and then it didn't match. So my first thought was, oh, darn it, I have bugs in my code, right? It doesn't match. Because his is running in production, everything's fine, so what could go wrong, right? So the next morning I got up and I said, let me just run it again because I like to waste time. So I'll run the same exact thing twice. And in the morning it worked. So in the morning it worked, and at night it didn't work. So it sounds like somebody's mutating global state. Now, before you accuse somebody of doing that, you better know, because you could be really offended. But somebody was mutating global state. So that was a side effect because in one of the date calculations, they kind of missed, there was a UTC conversion to normalize at the UTC time. So if I ran it in the morning, I would get the right date, but without the UTC conversion, where the UTC had already changed to a new day, at night it was a different value. And that's kind of a no-no in software engineering in general, but certainly in a functional programming environment. Again, the results here were 100% correct. To process a range of 1 month, we went from 16 hours to 30 minutes, so that's about 3% of the runtime. So if you've got programs that were written in the early days of Hadoop, this might be an interesting exercise to go through. Apply some of the principles of functional programming. Go through the checklist and say, whether I'm using a functional programming language or not, am I following these principles? And by not following them, have I introduced some of these kind of problems? And again, just because it's working doesn't mean it's working in an optimal way. And I think I have 1 minute left. That's all I was going to say today. So questions, comments, nonviolent objections, opinions? Okay, thanks.